Imagine standing on a quiet airfield. The sun is just rising, casting a pale glow across the tarmac. A sleek aircraft sits ready, not plugged in, not fueled, not tethered in any conventional way. And yet, when it starts, everyone in the room knows they are about to witness something that defies everything they thought they understood about physics. Maxwell Chikumbutso's self-powered aircraft isn't theoretical. It isn't a model on a desk or a simulation on a screen. Today, it is real, and it is ready to fly. Engineers, skeptics, and observers gather, cameras ready, instruments calibrated, expecting the impossible to fail. Most have already written it off as science fiction. Some even chuckle quietly, waiting for the demonstration to end in predictable disappointment. The pilot enters the cockpit. There is no sound of combustion, no hum of conventional engines. Only the subtle vibration of the aircraft's own internal energy system. As the canopy closes, you can feel the tension, half disbelief, half anticipation. Then the aircraft begins to move. Slowly at first, rolling down the runway, seemingly weightless, almost unreal. Instruments record power readings that shouldn't exist. The aircraft accelerates, picking up speed without the roar of jet fuel or electricity from charging stations. Observers start whispering, checking readings again and again. Every measurement confirms the impossible. The plane is generating the energy it needs to sustain flight, live, in real conditions. Takeoff is smooth, precise, and eerily quiet. The wings lift effortlessly, gliding into the sky as instruments continue to record stable, self-sustaining power output. Engineers and physicists in the room exchange stunned looks. Questions flood their minds. How is this happening? How can energy output remain consistent without an external source? Why does it obey gravity, yet seemingly defy conventional rules of fuel and power? As the aircraft ascends, patterns emerge in the readings that no one anticipated. Energy flows that should have fluctuated remain remarkably stable. Thermal imaging shows no significant heat loss. Power efficiency remains beyond known standards. This is not a minor anomaly. This is a phenomenon that challenges everything the aerospace and energy industries have assumed about flight and energy consumption. Observers begin to record every detail meticulously. Independent meters, thermal sensors, and high-speed cameras document the event. The aircraft executes maneuvers with precision, responding to controls as if it were a conventional plane, yet powered entirely by its internal self-sustaining system. Every calculation based on known physics is being rewritten in real time. And then comes the moment everyone feared and hoped for simultaneously. The aircraft hovers at low altitude, maintaining position effortlessly, before accelerating into a series of complex flight patterns. The engineer's whispers turn into stunned silence. The skeptics' smirks vanish completely. The realization sets in that this is not a trick, not a simulation, not a hoax. This is the first live demonstration of a truly self-powered aircraft. But the most important question remains unspoken in the room. If this aircraft can sustain flight independently, without fuel, without external charging, what does this mean for aviation, energy, and the future of transportation worldwide? Already, discussions begin, quietly behind the cameras. How can this technology be scaled? Could self-powered aircraft revolutionize commercial flight? Could this reduce reliance on fuel globally? Or is it a phenomenon so unprecedented that it will take years, decades, to fully understand and replicate? And while the world outside the airfield waits for official announcements, the aircraft continues to soar, proving silently, emphatically, that the boundaries of physics may not be as rigid as everyone thought. As the aircraft glides effortlessly, the focus in the control tent shifts from awe to analysis. Every sensor, every meter, every camera feed is being monitored in real time. The data is unprecedented. Voltage and current readings indicate the system isn't merely efficient, it's self-regulating. Energy fluctuations that should naturally occur are being smoothed out automatically, as if the aircraft itself knows how to maintain optimal performance. Engineers begin discussing the implications in hushed tones. If a single aircraft can sustain flight indefinitely, what happens when a fleet of these planes is deployed? Could long-haul flights across continents operate without refueling stops? Could emergency response and disaster relief be transformed overnight? Questions multiply faster than anyone can answer them. Meanwhile, the aircraft executes maneuvers previously considered impossible for a craft of its size and design. Tight banking turns, altitude adjustments, and sustained hovering, all without consuming conventional energy. Observers compare readings to standard aviation benchmarks and realize the margins are beyond current aerospace standards. It isn't just performing, it's outperforming. Suddenly, a minor turbulence spike hits. Normally, energy loss would spike and require compensation from fuel or stored power. Not here. The aircraft adjusts instantaneously. Its self-powered system redistributes energy internally, maintaining stability in a way that seems almost alive. Cameras capture the subtle glow of onboard energy cells pulsating in sync with the adjustments. Skeptics in the room start questioning everything they assumed about Maxwell's invention. Could it truly be a form of distributed energy generation on board? Or is there a principle in play that conventional physics hasn't yet fully grasped? Every engineer, physicist, and technician present is forced to confront the same uncomfortable realization. They are witnessing technology that may rewrite textbooks. By mid-flight, the aircraft begins to demonstrate endurance that was previously theoretical. Sensors indicate minimal degradation in energy efficiency. Thermal readings remain unusually low. Data logs suggest that the longer it operates, the more stable the system becomes. It's as though the aircraft improves with use, a self-correcting mechanism embedded into its design. Discussions shift toward practical application. If this technology can be scaled, global aviation infrastructure could be revolutionized. Remote regions, islands, and disaster zones could suddenly be accessible without dependence on fuel supply chains. Military, humanitarian, and commercial sectors begin to enter the conversation, though cautiously. The implications are too enormous for casual speculation. As the aircraft completes another precision maneuver and returns to the tarmac, cameras still rolling, the mood in the control tent is a mix of exhilaration, fear, and incredulity. Observers are not only questioning how this is happening, they are questioning the very limits of what they thought was possible. And yet, despite all the data, all the observations, and all the calculations, the ultimate question remains unanswered. If one self-powered aircraft can perform at this level, what happens when multiple aircraft operate in a coordinated network? Because if Maxwell's invention scales, the era of traditional aviation, dependent on fuel, batteries, or conventional energy infrastructure, may be on the brink of a radical transformation. The conversation in the control tent shifts from astonishment to strategy. If one aircraft is capable of sustained self-powered flight, what would happen if a fleet were deployed simultaneously? Could multiple units operate in synchronization, sharing energy dynamics, or would scaling introduce instability? Engineers start running mental simulations, comparing the live data with models they had relied on for decades, and finding almost nothing that aligns. Plans begin forming quietly. Not for publicity, not for a press release, but for the next critical phase, replication under varied conditions. Different altitudes, wind speeds, payloads, and operational durations. Each variable could reveal the limitations or the untapped potential of the system. Observers realize that until it is tested beyond a controlled airfield, the real capabilities remain unknown. Meanwhile, the implications stretch beyond aviation. Energy grids, transportation logistics, and even long-duration space travel could be affected if this principle can be adapted to other vehicles or scaled systems. Private investors and research institutions who had previously dismissed Maxwell's work begin sending discreet inquiries. The curiosity, once mocked, is now urgent and cautious. Back on the tarmac, the aircraft is refueled, not with fuel, but with careful recalibration of its internal systems. Each test begins identically, controlled, measured, and observed. The crew notes subtle behavioral changes as the system learns or adapts through repeated operation. Even minor disturbances, like unexpected gusts of wind or sudden load shifts, are compensated for instantly. Observers exchange glances. This isn't just about sustained flight anymore. It's about resilience and adaptability. The aircraft seems almost sentient in the way it manages energy internally, maintaining equilibrium without human intervention. The scale of what they are witnessing begins to sink in. A new kind of aviation technology, one that doesn't just fly. It optimizes itself continuously in real time. Questions that had never been asked before start circulating. Could a fleet of these aircraft operate autonomously, indefinitely? Could supply chains be reimagined if cargo planes no longer require fuel stops? Could entire industries, long dependent on fossil fuels, face disruption in a matter of years rather than decades? And still, the central mystery remains, the mechanism behind this self-sustaining power. While instruments measure inputs and outputs with precision, no conventional theory fully explains the phenomenon. Maxwell's device isn't violating physics. It's operating at the edge of what conventional physics can predict. The room grows quiet as the aircraft begins a final maneuver. Cameras capture the perfect glide back to the runway. Observers know that what has just occurred isn't merely a demonstration, it's a paradigm shift. As the aircraft settles onto the runway, the tension in the control tent is palpable. The successful landing isn't a conclusion, it's a starting signal. Everyone present knows that replication, scaling, and real-world application are the true tests, far beyond the controlled environment of this airfield. Plans for extended flights are drafted quietly. Longer distances, higher altitudes, payloads approaching operational limits. Each new test designed to push the aircraft not just physically, but conceptually, challenging the boundaries of what self-powered systems can achieve. Data collection becomes almost obsessive. Every fluctuation, every micro-adjustment, every thermal gradient logged with millisecond precision. Meanwhile, discussions about networked operations emerge. If one aircraft can manage its energy autonomously, what happens when multiple units are coordinated? Could energy distribution occur dynamically between aircraft in flight? Could fleets adapt to external conditions collectively, optimizing efficiency in ways that traditional aviation never could? These questions shift the experiment from isolated innovation to systemic transformation. External observers, previously skeptical, are now whispering about potential applications: disaster relief without fuel dependency, autonomous cargo transport across continents, emergency medical supply flights in regions with no infrastructure. The implications extend beyond aviation into global logistics and energy distribution. Inside the lab, engineers begin theorizing new flight patterns, inspired by swarm dynamics and biological systems. The aircraft behaves less like a machine and more like a living network, self-correcting and adapting to variables in real time. Minor disturbances, previously seen as potential failures, are now treated as data points for continuous optimization. The team debates secrecy versus exposure. Public attention could attract funding, collaboration, and rapid development, but also scrutiny, interference, and potential exploitation. Each member understands the stakes. This isn't just an experimental aircraft. It's a technology that could redefine energy, mobility, and the very limits of engineering. A consensus emerges. The next phase must be deliberate, calculated, and verifiable. Flights in uncontrolled environments, varied weather, and longer durations are scheduled. Data will be peer-reviewed. Independent verification will be sought. The objective isn't just demonstration, it's proof. Proof that self-powered aviation can exist, not as a concept, but as operational reality. As dusk falls over the airfield, the aircraft rests quietly, its subtle glow a reminder of what has been achieved and what lies ahead. Every observer, from engineers to physicists, knows this is just the beginning. The world has glimpsed the edge of possibility, and the next experiments will determine whether humanity is ready to step beyond it. Night settles over the airfield, but the lab is alive with quiet intensity. Teams remain at their stations, poring over every data stream, every microsecond of flight telemetry, and every thermal and power reading. No one speaks louder than necessary. The magnitude of what they are witnessing demands focus, not chatter. Plans for extended, multi-day flights are drawn up. Engineers simulate scenarios, high-altitude endurance tests, cross-continental routes, and operations in extreme weather conditions. Each scenario is analyzed in meticulous detail, looking for any potential weaknesses or patterns that could be exploited or that could fail. The aircraft's behavior is unpredictable in ways no traditional flight models can fully capture, yet repeatable enough to be measurable, a paradox that keeps the team both enthralled and cautious. Discussions turn to fleet coordination. If a single self-powered aircraft can adapt autonomously, could a dozen or 100 synchronize their operations? Could they share energy loads dynamically? Could emergent behavior appear when multiple aircraft interact, producing efficiencies or patterns impossible to achieve individually? The questions grow exponentially with each additional aircraft considered. Meanwhile, whispers outside the lab begin to circulate. Private aerospace firms, research institutions, and even governmental agencies start inquiring discreetly about the technology. Skeptics who once laughed are now asking for observation opportunities. Maxwell's invention is no longer just a curiosity. It's a potential disruptor with global implications. Inside the lab, minor disturbances are intentionally introduced: wind gusts, simulated mechanical strain, and variations in payload. Each time, the aircraft compensates perfectly, distributing energy and stabilizing without any external input. Observers start to theorize. Perhaps the system isn't just self-powered, it's self-optimizing, a new class of adaptive energy technology that challenges fundamental assumptions about power, flight, and autonomy. The team debates public demonstration versus controlled validation. Exposure could accelerate funding, collaboration, and technological progress, but also invite scrutiny, patent disputes, and political pressure. The decision is unanimous. Meticulous documentation, peer review, and stage scaling are critical before any public release. Late into the night, the aircraft remains on standby, quietly pulsing with energy, a silent testament to what has been achieved and a warning of what may come. Everyone present knows that the next phase of testing will determine whether this is a fleeting anomaly or the dawn of a new era in aviation and energy. As dawn breaks over the airfield, the aircraft sits quietly, its subtle glow a symbol of both achievement and possibility. The tests have confirmed what once seemed impossible: sustained, self-powered flight is real, repeatable, and resilient. But the true journey is just beginning. Scaling, replication, and real-world deployment will test not just the technology, but our assumptions about energy, mobility, and the limits of engineering itself. Maxwell's invention doesn't just challenge the rules, it rewrites them. The world may not yet be ready to fully understand it, but one thing is certain: the era of self-powered flight has begun, and humanity is witnessing a breakthrough that could redefine the skies forever.